I'm V. I'm from OWU, and my project is applying epilepsy on a network. So, just to get into it real quick, what exactly is epilepsy? It's a broad group of disorders, a sort of umbrella, but they all share one common characteristic, which is recurring seizures, which is just a lot of activity in the brain, as you can see by this EEG trace of different parts of the brain. Pretty nice here, and then just gets all wild when it undergoes an epileptic seizure. We understand a lot about what these seizures are, but we still have a ways to go with understanding why they come up and a lot more about the mechanics of how they work. So if you're a clinician, which I don't think any of you are, but if you were and a patient comes in with epilepsy, what you're looking at now is basically the cutting edge of what our current technology allows us. They stick a bunch of electrodes in the brain, monitor those until you see a lot of activity, and then just map out where it spreads, hopefully in order to get a sense of where it starts, where it spreads to, and then make a bunch of incisions in the brain between those two areas in the hope that this will impede the seizure from spreading. It's not targeted, it's not really refined, it's a really sort of crude method of going at it, which really emphasizes our crude understanding of how it spreads. Even worst case scenario, they would take out the entire chunk of the brain where it starts, which can have unforeseen consequences. Okay, so what we want to do is to model this in order to get a much more refined tool set. And luckily we don't have to start this from scratch, because in 2014 there was a paper published which had a bunch of equations, which had a system of equations which modeled a seizure event. And the way that they approached it was to use a phenomenological approach. I said that right. If you look at this voltage trace, you can sort of parse out three distinct features. First is when the part of the brain undergoes a seizure, the voltage drops like that. Secondly, you see a lot of fast spikes when a seizure is occurring, and you also see spikes between and before seizures. So in math words, this is what this is modeling. This is a typical output of it. You can see some like feature similarities with them. So just going a little bit more, these first two here model the spikes going on during the seizure, the fast ones. This variable here determines whether or not it's actually in a seizure state. And then this last set models these spikes between and before seizures. You might notice I didn't mention anything about the DC shift. Keep that in mind, I'll get back to it. So, digging a little bit deeper, if we look at the phase plane of x1 and y1 variables, we notice three different equilibria points, which I've emphasized here. The first one is a stable node, attracts any trajectory going around it here. The second one is a saddle point, so anything approaching it from below gets pushed down, anything from above gets pushed up. And then this right here is another stable point, so anything goes in towards that and most of the time sort of spirals in. But that's for one value of z. As you saw, our equations are a lot more connected than that. So what happens if you change z? Well, you see right here for a decreasing value of z, the red null climb of this system gets shifted down until eventually here, these nodes and these equilibrium points annihilate in what's known as a saddle node bifurcation, because that's a saddle and that's a node. And once the system reaches a point where this equilibria point passes the trajectory that would be going down here, it gets pushed up here and starts spiraling in and orbiting, which is those ripple effects that you see in a natural seizure trace. Another important thing to note here is before this point gets here, you see x1 is somewhere like right here. But after z reaches a low enough value, x1 goes up to here. That's that DC shift that we are looking to reproduce in the first place. Now, to make things even a little bit more complicated, z isn't just a static variable we can change. The value of z is determined by the value of the other variables as well. And that results in this sort of cyclical oscillatory nature between these two, where z goes down, which makes x1 go up, which makes z go up, which makes x1 go down, which makes so on and so forth. So yeah, that's what we have, that's what this system as published can do, and that's how that works. But what we want to do is to expand this into a network to take a bunch of these chunks and put them together. So the way we do that is to use something known as network theory, a branch of graph theory in mathematics, to analyze how this functions on a network that resembles the brain. Where did all those slides? Okay, I have no idea why that happened. Yeah, so we would prefer to do this on a human brain, but because of our technical limitations, we don't have what's known as directionality of the human connectome. So instead, we use it with a cousin of ours, the macaque. Lucky for us, the macaque brain is already used in neuroscience research, a lot of visual testing, because on the broad scale, we believe that their brains are fairly similar to ours. So it's a fairly similar assumption to make. So basically, that's what we did. We took these equations and started the seizure back here by forcing the z value to be lower, and then saw how it spread throughout this entire network. And you can see here, red means it's seizing, not red means it's not. And you see that it starts here, a little bit of a lag, and then it generalizes throughout the entire network. What we noticed is that one certain connection seemed to act as a sort of bridge between here and the rest of the network. So we thought, okay, well, what if we snip the connection between here and that node? Well, this is what we got, where the seizure not only didn't spread to any other node, but just kept blinking alone, sort of sad. And this really is the proof of principle that we sought out to show, that we, with fairly minimal damage to the brain, just removal of the connection between one chunk of the brain and another, we were able to prevent this from spreading. If this were a clinical trial using our current tools, probably would have cut a few more of those or even taken out this entire chunk. So what we want to do is to figure out if our parameter choices are viable or realistic. We can do that by comparing it to real data. And we also want to figure out what it is about that connection that we snipped that was so crucial to its spreading throughout the entire network. We believe our hypothesis is that it's something to do with what's known as the betweenness of that edge. In so many words, it's sort of how much of a bridge that edge acts as between two different communities. So if a seizure started here, it would need to go through this edge to reach over here. So that has a high between us. And I would like to thank these folks and IH for funding me and y'all for listening. Do you have any questions?
Thank you, B. Questions?
Is there enough research data to know sort of where the seizures tend to start, sort of like what part of the brain they're often starting?
I don't believe that it's really a general trend. It's really specific to from patient to patient, because a lot of seizure has to do with like head trauma or specific things that might influence how healthy different parts of the brain are. So I don't know if there's a hard and fast way to say that.
Is there a way to sort of know after someone, like can they figure it out for a particular individual after they've had seizures?
Yeah, which I don't know why there's like 20 blank slides. There were 10 minutes ago. But yeah, that's basically
so they
what.
Can afterwards.
Yeah, you probably can't see it from there, but like there are red stars which indicate a seizure started here, and then red dots, which means it spread to there.
Go forward a couple of slides. Well, I think it's the one with lots of, yeah, stop there, right? So just kind of qualitatively looking at it. So the left there is what the equations produce, the graph, and then the right is an actual trace for.
Yeah.
So just kind of looking at it qualitatively, it looks like in the actual seizure, the spikes are kind of above the baseline, and in the model, they're below the baseline. And what's up with that?
I'm not entirely sure. This is sort of an aggregate sum of several of the variables to try to reproduce that. And I think the main thing is just it's not exactly doing this. It's just reproducing sort of the feel of the equations, how they act in general.
It seems like there's a microsite or something.
I don't think the people who create this model care about that.
It's interesting.
Yeah, I just don't think they thought it was relevant. And I don't know if it necessarily is. I mean, this is debatable, but
It's like not as when it's like.
this isn't even the voltage trace of the individual neuron. It's just EEG, so it's like the collective. Yeah. So, I mean, I think it's more interested in like, is the system going haywire or not?
The timing is much more important for the shape.
Yeah.
As an outsider, but
Those don't match.
okay.
Yeah.
If you squint, sort of. Yeah.
The picture you had of the brain with the network on it, you said that you were running this on this creature here, but I mean, this isn't like you ran it on a real brain. So what makes this network that you put on top of this brain actually correspond to a real macaque brain?
So the way that we got this network was from a database, which I don't know what sort of tests they did. I think it's like DTI, something, whatever. They ran like, it's sort of the sum of several different experiments, several different people mapping out little connections between 3 or 4 regions, and then trying to compile all of those together. So this is representative of the broad connections in an actual macaque brain, but like we didn't make it ourselves.
It's like a huge effort actually within the neuroscience community to get this data. This is, like V said, aggregated over dozens and dozens of studies where they'll inject some sort of, I don't even know all the molecular details, but they'll inject a marker into like one part of the brain, and it can only go through the axons. It can't get outside those neurons, so it migrates through the axons, and wherever it ends up, you know that it's sending a connection to that region. But it's really, really tedious, so each study can only do a few brain regions, and then you have to aggregate them all in this huge database.
So it's a incorporating known directionalities within the actual cognitive.
Right. And with the human brain, we can't do that because, it's not equitable.
IRBs would be.
Yeah, they would not be happy with that. So you can only do so-called diffusion tensor imaging in the human brain, but that doesn't give you directionality.
Black
Okay.
market brain studies.
The dark web.
Web.
Cool, let's thank V again.